Hello, I'm super excited to be speaking to you all. I've learned a lot from past talks at this meetup and also from the Max conference talks. I'm going to be talking about some of the work we've been doing at Runway, building next generation video tools, specifically incorporating machine capabilities into the video editing workflow. And I'm going to be focusing on the green screen product, which is a tool for automatic rotoscoping. So isolating specific objects from a video and tracking them over time. But also I'm going to be talking a bit more broadly about some of the infrastructure work that we've been doing to support future machine learning models on video that we are planning to be releasing. I'm going to do a quick demo of green screen just to show you what the general workflow is like before jumping into the technical details. So this is the green screen interface, and here are the videos that I've already uploaded. I'm going to pick this dancer video to test, and here I want to segment the dancer out of the background of this video. And I might want to do that because I want to move this dancer in another video, or I want to apply specific transformations just on a dancer. So the first thing I'm going to do is I'm going to add some include clicks to isolate the subject in the video. And now I'm going to start previewing how the mask will propagate over time. So the moment I click preview, we're going to start requesting the mask segments from this video based on the keyframes that I've created here. So here I can see I have my mask tracking the subject throughout the rest of the video based on the one keyframe I created at the beginning of the video. If I see any parts that are not where the mask is inaccurate, then I can add more clicks in other frames of the video to add additional guidance. So for example, in this frame, I see that these parts of the legs is not covered. So I'm gonna add 2 more include clicks, and this creates a better mask. So I can repeat that process as much as I want, just to further improve the mask. But once I'm happy with the final mask, I can now export. And there is a few different options for exporting. I can export with a chroma key background that I can then remove in the editing software, or I can export directly the alpha mask that then I can use as a Luma Mate in some other video editing software. I can also add feathering to the mask, so this tends to work better for compositing purposes, so that there is not too much contrast between the foreground that we composite and the background. So essentially we divide the task of segmenting an object in the video into 2 sub-problems to make our job easier. The first task is just operates on a single frame of the video, so it's really an image segmentation task. And the idea is we want to generate as high quality of a mask on that single frame as possible and as controllable as possible. So we train a model that incorporates user input in the form of clicks on the object. So the user can add clicks on the regions that they want to mask. And we also have exclude clicks. So the idea is that they can, if the model makes an incorrect prediction and includes a region in the mask that's incorrect, then they can click there with an exclude click and remove that part from the output mask. And again, the big challenge here is just controllability. It's just making sure that we incorporate the guidance from the user actions into the output of the model without requiring also the user to provide too much of that guidance. So ideally, the user should only have to click like once or twice to mask the object in the video. But if they want, and if it's an especially tricky object to mask, then they can provide an arbitrary number of clicks to further refine the mask. The second task is a video task. So it's basically propagating the masks that have been created on like a very small subset of the frames that the user has created through clicks to the rest of the video, and having a temporally consistent stream of masks, kind of isolating the object in every frame of the video. Here, like consistency is like the main priority. We don't want them to have too much flickering. We don't want the mask to appear and disappear throughout the video. Like that would create an output that's not acceptable for professional usage. And we also have like more efficiency concerns since we have to segment the object in every single frame of the video, and we need to return the results for preview to the user as fast as possible. So it needs to work at real time or near real time frame rates to be able to do that. So we'll first talk about the refinement network, and the job of the refinement network is to isolate the subject in the frame of the video. Uh, we provide the ability to, as I mentioned, have include clicks. So like I want this region to be part of the output mask, and exclude clicks, which tell the model to remove a region from the output mask. Uh, and this is different from like most of the segmentation models out there are either semantic segmentation models, so they can identify objects from a preset number of categories that are in the original data set, or saliency-based methods. And saliency-based methods basically separate the foreground from the background. But we want to have something more flexible that allows maybe not isolating the most salient object in the video, or maybe isolating a specific part of an object, or even for objects that appear and disappear throughout the video. We like a saliency-based method would not work as well, since it would always try to find a foreground to isolate. Um, so those methods work fine if the background is kind of out of focus or blurred, like if it's kind of the separation between foreground and background is very obvious. But we want our tool to work on the more difficult cases, and for that, it's necessary to incorporate user input because we don't know what object the user wants to segment, and the model might make mistakes that the user would have to correct afterwards. So we follow a fairly standard architecture for our refinement network. It's a UNet architecture, which in the past few years is kind of the standard architecture for segmentation models. It's an encoder-decoder architecture. The encoder basically generates a feature embedding from an input image, and with the decoder, it takes that embedding and generates the output mask, isolating an object in the image. And there is also skip connections between the encoder layer at each scale directly to the corresponding decoder layer, just to transfer context directly from the input to the output without the downsampling that happens when generating the embedding. What's different about the refinement network is we also, as I mentioned, we incorporate user input in the form of clicks. So we basically pass another channel to the model that has that represents those clicks that the user has made. In terms of training data, since the refinement network only operates on images, specifically on frames of the video, we can train it on image segmentation datasets, which generally there's more of them than video segmentation datasets, and they're easier to create. We're kind of augmenting those image segmentation datasets with synthetic user clicks. So as I mentioned, the refinement network needs to incorporate user input on the mask generation. So training just input frames and mask pairs is not going to be enough. We need to generate a paired data set that includes both the input image and the clicks as input, and then generate the resulting masks based on those. So we created a synthetic dataset where we basically simulate how users would interact on the given frame to isolate an object. So we want to also capture a wide range of clicking behavior. So not every user is going to behave the same. Some users are going to make 1 or 2 clicks on the object. Some users are going to make a lot of clicks. Some users are going to make just include clicks. Some users are going to make both include and exclude clicks. So we had to make a kind of variety of assumptions about how users would interact with this interface. Like another assumption we make is that users are, once a user clicks on a specific part of the image, they're less likely to click on that near the same region again and the second time. So essentially every click creates a repelling force around it in the way we predict where the user is going to click next. Okay, so moving on to the next subproblem that we described. So the refinement network solves the problem of isolating an object in a single frame of the video or in a few individual frames of the video. And then what we want to do is propagate those keyframes to the rest of the video so that we have a temporally consistent mask that tracks the object throughout the entire video. Obviously, making that same process on every single frame of the video is very time consuming. So ideally, we have a smart way to interpolate between those very sparse keyframes that we make to the rest of the video. So this is the task that the propagation network is solving. This is another separate neural network. And the main task of this neural network is given the keyframe mask that the user has generated by clicking on individual frames of the video, learn to interpolate in a smart way those masks throughout the rest of the video. Those keyframes might come after a given frame or before a given frame. We always use the two keyframe masks that are nearest the frame that we are looking to mask. And this way we maintain consistency as we're tracking the object throughout the video. The architecture that we use here is pretty similar to the refinement network. It's also a unit architecture, but instead of encoding just the input frame, we also encode the keyframe that we want to match against. And then we use a space-time attention mechanism that basically identifies how relevant each given frame and each part of the keyframe is to the frame that we're trying to mask. And we also, an additional thing we do is we incorporate a lightweight layer at the end of the decoder, whose job is to smooth out the edges of the final masks to handle hair and other like semi-transparent regions of the output, just so it's more suitable for compositing. Say we want to move the subject to a different background, and a binary mask in that case doesn't work as well. So since we needed to run the propagation network on every single frame of the video, the performance requirements that we have are a lot stricter than in the refinement network. In the refinement network, we only run inference on a single image, which tends to be quite fast. Unlike that, on the propagation network side, we really need to preview how the mask will look on every single frame of the video. Traditional rotoscoping tools tend to be quite slow at this, so they might take hundreds of milliseconds or seconds per frame of the video. We wanted our tool to be a lot faster than that and allow this like greater level of interactivity and quicker feedback loop between the user and the machine learning model, just so that the user can easily kind of make changes and iterate on the mask that they're creating. Being a cloud-based tool means that we can leverage GPU instances for this task, unlike a lot of the traditional tools that rely on local compute, where running deep learning models tends to be a lot slower or requires to run at like a low resolution to get interactive frame rates. But even so, it was quite a bit of a challenge to get them all to run at real-time frame rates. We were initially using a PyTorch implementation of the model. That we used PyTorch to train the model and like build a kind of data set and data training augmentation pipeline. But for the purposes of actual inference and model serving, that the original model tend to only be able to do real-time frame rates around like 360p resolution. We tried a few different strategies to kind of like on the UX side to accommodate for that. We tried previewing the video at the lower frame rate. That worked, but it led to kind of a suboptimal user experience because the user will not see all the frames that they're segmenting during preview and during the interactive part of the process. And so they might export a video and then find out that one frame that was not included in the subsample of the frames that we're previewing has not a good mask. And so they have to go back, and they also have no control over those masks that occur in the frames that we're not showing in the preview. So ideally, we want to be able to preview every single frame of the video. So what we end up doing, we move the model to TensorRT, which is an inference-specific model framework made by NVIDIA, and that led to a significant improvement in performance, around like a 4x speedup. That was in combination with a few other things, like making sure that we reduce as much as we can any memory reallocations, and having faster pre-processing and post-processing and so on. But basically that enabled us to run inference at around 60 frames per second, which is like faster than real time for most input videos, which tend to be like 25 or 30 frames per second. Of course, there is additional overhead in the whole pipeline. So 60 frames per second is not the final frame rate that the user is seeing inference run at, because we have to first, every request that the user makes for a specific segment of the processed output, we need to decode that segment from the original video. We need to process it through the model. Then we need to encode it back to a compressed segment that we send to the client, and the client needs to decode that. But in general, like we achieve real-time or near real-time user experience as you're using the green screen and as you're segmenting your object through time on the video. One of the challenges that we faced as we trained the propagation network was creating a high quality video segmentation data set. So dense labeling of frames in a video is very time consuming and expensive to perform. You need to basically create an annotation for every single pixel of every single frame of the video. There is ways of speeding up that process and incorporating a machine learning model in that loop, but it tends to come at the cost of the quality of the segmentation data set. So in order to address this, we created, again, a synthetic data set in order to train the propagation network. And the idea here was to collect a variety of stock footage videos that were shot in green screen, and then isolate the subject from those videos, which is easy to do with like a chroma key filter and some spill reduction as well. And that separates the foreground subjects from those videos. And then we composed those to completely different videos that were unrelated, sometimes creating kind of very absurd composites, as you can see. But this allowed us to kind of scale the amount of data that we had to work with, because we could combine like hundreds of different subjects with thousands of different videos as backgrounds. And so we composed those subjects in those different variety of contexts, and we use the resulting alpha mask for compositing as our ground truth segmentation. Finally, we had to make some compromises and trade-offs for deploying the propagation network. First of all, we generate the masks at a maximum of 720p resolution for just previewing purposes. On the export side, we process at the original resolution of the video up to 4K. 720p seems to be like the right kind of strikes the right balance between it's a good enough resolution for getting most of the details right for previewing purposes. We might get some imperfect masks for small items or imperfect edges, but for the most part, it closely matches what you would get at a higher resolution. One other trade-off that we made is that we needed to pick only the two nearest keyframes when trying to predict the mask for a given frame. We could, in theory, incorporate as many keyframes as we want and match them with the current frame. But in practice, like each of those keyframes comes at the additional compute and memory usage cost. And to get more predictable runtime and memory usage, we only pick the two nearest keyframes, and that covers the vast majority of cases that we encounter. So the second demo I'm going to be doing is of SQL. So SQL extends some of the work we've been doing with green screen, but it provides a more general video editing interface that allows you to do, in addition to the ML-based capabilities, you can do some more of the traditional things you'd expect from a video editor. For example, manage clips in a timeline, or apply visual effects, or apply transforms over spatial transforms of different layers in the video. So I'm going to take the same dancer clip, I'm going to go to green screen and generate a mask. I'm going to save my mask. So now I'm back on the SQL interface, and again I've isolated the mask. I can say duplicate the layer here and remove the mask from the background layer, and now I can now that I have the mask isolated and also the background layer, I can apply separate transforms on either of them. So one thing I could do, for example, is I could clone the dancer. Another thing I could do is I wanna let's bring the dancer back. And now I can apply effects specifically on the background that should not affect the dancer. So say I want to blur the background to kind of give more focus to the dancer. There's a few different effects I can consider here. For example, I can say just add a blur. And so now I have a blur that is applied anywhere but the foreground mask that I've generated. So this is just a glimpse of the things you can do with SQL. The general theme being you can combine the ML-based functionality with the more traditional video editing functionality. So a lot of what we do in SQL is we apply ML models to the frames of the source videos that we bring to SQL to create basically different views or different metadata associated with that video. So, and these are incorporated for various purposes. So like if you have optical flow for a video that we can predict, you can then generate some you can retime the video and interpolate between frames. If you have depth, you can add like a series of effects like bokeh effect that incorporates the depth information into creating the effect. And one of the challenges there is that like we want to have like a very easy way to incorporate and bring new models and functionality in SQL without changing too much on the way on the front end side we handle those new model functionalities. And so we've developed a common abstraction around HLS that basically every output of a model can be requested in the exact same way. So we define like a Python interface that basically specifies like how to process a specific segment of a video with a machine learning model. That could be an optical flow model, a depth prediction model, or a stylization model, or there's a variety of different models that we use inside SQL. And the idea is that by just defining that function for processing a segment of video, we then have functionality that comes from our model streaming SDK for automatically generating playlists, creating different presets in bitrate and resolution, creating storyboards that basically summarize how this ML model processes this video, or requesting individual frames of the video when we seek to different parts of the video. And I guess the main thing to consider is that the front is completely agnostic to any implementation details for the model. It simply just requests a different stream from our backend service. That's it. I don't want to run out of time. So I guess the last thing I want to mention is we're still getting started. Like this is just the foundation for a much larger suite around video tools. So if those challenges sound interesting to you, we're hiring a lot of folks on the video engineering side. So definitely feel free to reach out to me and see if there's any way we can work together. Thanks so much for your time.